Anyway, so today I have the great pleasure to introduce Dr. Costas. Is it Busch?
Yes.
Yes. Okay, Costas Busch. And Costas is a new faculty member here at Augusta University. He was got his PhD at Brown University, which has actually got a lot of really cool PL people at Brown. And his research interests are in the areas of distributed algorithms and data structures, design and analysis of communication algorithms, game theory, and blockchains. And I think he's going to be talking about game theory and sort of a mixture of these today. And so, yeah, so please take it away, Costas, and thank you.
All right, sure. Thank you very much, Harley, for the introduction. It's a pleasure to be here and to give this talk. So, the last time I gave a talk at Augusta University was on a different topic. It was on transactional memory. This time I want to show another aspect of my research, which is algorithmic game theory. And I have been working on this topic for several years, and it has been on and off, depending on the problems we try to solve. And but the main theme of my research in that area has been bottleneck congestion games, and which is what I want to talk about today. So I will start the talk with a mild introduction in algorithmic game theory. Basically, I will explain what it is, and then go more in depth in my research, which is on bottleneck congestion games. I will define the game, and then define the results, which is basically we computed some Nash equilibria very fast. And there are two techniques to do that. One is on splittable equilibria, and the other is a splittable equilibria. And I will go into these details later. And finally, I will finish with the conclusions. So now I will start with an introduction on game theory. I'll just describe the general area, what it is, and what kinds of problems we're looking at. So first of all, let's look at game theory. So game theory has been around for many years, and it's a very well established research area, not only in computer science, but also in mathematics and economics. And basically in this area we have we have players. Players we can imagine are like people, or it could be agents, or it could be programs which interact with each other. They are sharing something though. They are both in a common environment, and their actions somehow are orthogonal. So when one player takes an action, it may hurt another player. So we assume the players are rational in the sense that their actions are based on knowledge, and they always try to improve something. So they have some benefit which they want to improve. However, in most of the cases when we study game theory, we talk about non-cooperative players, which are the kinds of players which basically they don't collaborate to achieve the goal. Basically, they're independent, and they try to achieve a goal that benefits themselves, but not the others. And in fact, when one player tries to take an action to benefit himself or herself, it may hurt another person. So a classic, so if somebody tries to describe game theory, the classic example that comes into mind is the prisoner's dilemma problem. And that problem exhibits the non-cooperative behavior and the rational behavior of the players. And also it exhibits the involved costs. So in this example, simple game, we have two players, A and B. And those are two malicious kinds of players. So they did a bad act and they got caught. And so they did this act together, but they didn't coordinate for how to resolve the situation if they get caught. So they got caught. And now they're being interrogated in separate rooms. During the interrogation, they have two options: either to stay silent, don't really reveal any of what they did, anything of what they did. Basically, they don't reveal what they did and what their collaborator did, or betray. So in betrayal, basically, they admit to their bad action. And there is a benefit for it. For the betrayal, there is a benefit. So if they betray, they don't get any prison time. So here, this number 0, in the case of betrayal of A, so if A betrays, gets 0 years in prison time. However, the other person B gets 3 years in prison time. So if they both stay silent, so they don't admit to their actions, so they get the minimal penalty, which is only 1 year in prison time, because basically there is no proof that they did it. However, if both betray, if both admit to their actions at the same time, they both get punished 2 years in prison time. So this shows the different costs for their actions. And actually, the action of one can hurt the other, as it shows when one betrays and the other stays silent. So the betrayal has 0 prison time, silence means -3 prison time. So there are 2 states where one gets maximum benefit, 0 time, prison time, the other gets minimum benefit. However, there are 2 other interesting states. This state I have highlighted in the diagonal is the most likely outcome, well, because they are not cooperating. So they're both alone in the derogation room. They don't know what the other is doing. So they have to assume the worst scenario. And so to get the least punishment, they admit to their crime and they get only 2 years of prison time instead of the 3 that they would get in the worst case scenario. So that will be the most likely outcome for this game. So for this game, I mentioned this game, it's not so much related to the other games I will talk today, but just to introduce the idea of cost and rationality for the players. So generally, when we talk about in game theory, we have different players. So here I talked about games with 2 players, but you can have more than 2 players. And in many circumstances, players take turns. So we have one player making a move in the game, then the second player making a move, then again, first player makes a move, and so on. These moves can alternate. And we have such games, for example, of course, somebody can imagine the real, like board games. Okay, we can have regular games that we play with small groups, but we have some other real life situations. For example, we have auctions. So in auctions, some people are bidding for different items. So, for example, a player 1 may bid for an item, and that can increase the price of the item. And now the player 2 is going to make another bid. Then that will force the player 1 to make a bid again. And then player 2 will make another bid, and so on. So this goes back and forth until they reach the final price, where no player will make any further move, and then the item is being sold. Other cases like that in real life where we have players interacting is dividing shared resources. For example, we may have a property that needs to be sold, and then one person can get a part of the property, another person may get another part of the property. However, these 2 can have a different evaluation of the property. So somebody, for example, may evaluate, say, the value, if the property has some lake or water, and they may evaluate that more than having land, where another person may like to have more land than water. So therefore, they have different perspectives on what they try to share. And in other cases, in bargaining, when we try to buy an item from a store, we bargain with the seller, so the buyer bargains with the seller until they reach the price where they both agree. And there are other situations where we have this kind of interactions where there is some cost. Every player has a cost, and they try to minimize their own cost function. So generally speaking, so we have these alternating moves of players. And what generally happens that when one player makes a move and tries to improve their own benefit, that can hurt the benefit of the second player. Now, when the second player makes a move, this can go back to the first player. So the second player might improve, then the first player gets worse. And this goes back and forth now. It can go back and forth for many rounds. So hopefully, this situation stabilizes, and then we reach the end of the game. And at that time, you get the final action. For example, you sell the item if it is in an auction. But generally there might be games where we may not have a stability. This may never ever converge. Right? So in the games that I'm going to discuss today, we have convergence, and this convergence actually reaches to a state that we call it the Nash equilibrium. Okay, so that's that state where all the players have converged, and they cannot improve anymore. We call it a Nash equilibrium. So Nash equilibrium basically is a case, is a state of the game where every player has reached a minimum, a local minimum, where it's a state they cannot improve anymore. And so, for example, if any of them tries to change, then they will have less benefit than if they stay in the current state. So that's a Nash equilibrium. There are other types of equilibria. There is another type of a very equilibrium which people use is Pareto equilibrium. Pareto equilibrium is similar to Nash equilibrium. However, it is an equilibrium where if a player moves, he's going to hurt another. So if a player is to improve, this can only happen by hurting others. So it's like so Pareto equilibrium is a Nash equilibrium, but an altruistic version of the Nash equilibrium. So any further move will only hurt other people. So, but Nash equilibrium doesn't care about hurting others. Okay, so Nash equilibrium is worse. It's not as altruistic as the Pareto equilibrium. So today I'm going to focus on Nash equilibriums, and I'm going to give some examples with games. So let's go now to the computer science aspect of game theory. This is called algorithmic game theory. And this area started in 1999 with a seminal paper by Koutsoukias and Papadimitriou with the title Worst Case Equilibria. So that paper tried to give quantity to the quality of certain aspects of game theory, and especially the quality of Nash equilibria. So in this game they studied a very simple game actually, which reflects to many interesting problems in computer science. So they have two nodes in this game, and there are many parallel edges connecting the two nodes. So those are parallel links. So now every player, there are players here. So I have m parallel links in the game, and there are n players. So every player tries to do something. So every player has some demand. We call it demand di. And it wants to send this demand over the link. So suppose every player starts from this source and wants to send the demand over the links to the destination. So from the left to the right. So a player may decide to send all the demand on one link only. For example, player I has decided to send all the demand di on the top link. Player K has decided to send all the demand on the middle link. Now players J and players L have decided to send the demand on the same link. So some of these links can be shared by the players, and that makes it interesting. Otherwise, they wouldn't interact with each other. So what is a player cause? So a player wants to avoid interacting with others. So like a player I is in an ideal situation, doesn't interact with others. Like player K is in an ideal situation, doesn't interact. And player J and player L are in a less ideal situation because they're sharing the link. And sharing may not be good because we can think of it from a network point of view. If J and L are sharing a network link, then if they're using the link to send information, then it will take more time to send information because of the sharing. But this scenario can represent other problems also. For example, it could be that every edge could be a resource they're using. It could be, for example, that each player has a task to solve, and each link corresponds a machine used to solve the task. So sharing a link will correspond to sharing the machine to solve the task. And so sharing is not beneficial. Being alone is better. But the thing is that if the number of players is more than the number of links, it's unavoidable to share. They have to share. So if they're going to share, they want to do it in a way that it minimizes the sharing. Okay, so the player cost to express this minimization problem is so if a player I, or for example player J uses this edge, so the cost for player J is the sum of the demands of J and L. So here, for example, the cost for this link is the sum of the demands for these two players. For player I, the cost is a DI. For player J, the cost is DJ plus DL. And in that way, we form the game. So each player wants to minimize that cost. They want to minimize the sharing. And let's see what they did. So this kind of game. So we can let these players play in the sense that each player can pick an edge, a link. And if it's not good, they can pick another link. So if they see some other link is better, they can switch to the other link. And so, so therefore players can take turns. For example, player I first can pick a good link. Then player J can pick a link and so on. And if player I is not happy with the current choice, then player I can switch. And but when the player I switches, maybe it hurts other players. So then another player may want to switch again. And then this can go back and forth until it stabilizes. So these states where they stabilize exist. Actually, they have shown that there is equilibriums. These are Nash equilibria, basically. There are states where no player wants to deviate from that state. Here I show some example sets. So I have 4 players. I have 2 links only. The top link is used by player I and K. The bottom link is used by player J and L. So imagine the demand for I is 6, the demand for K is 2, the demand for J is 5, and the demand for L is 3. So the cost of each player on the top is 8, because 6 plus 2, that's the total load on the top edge, is 8. So that's the cost of each of these players, I and K. The cost on the bottom link is also 8, because 5 plus 3 is 8. So both the loads on these edges are 8. Now, notice that this is an equilibrium because no player wants to change state. For example, if I switch to the bottom link, the cost on the bottom link will become 8 plus 3, 11, which is higher than 8. So I doesn't have any reason to switch. Similar, K doesn't have any reason to switch because if K goes to the bottom link, the cost it will observe will be 10, which will be more than 8. So it's better they stay. So all of them have benefit to stay. So they just stay there. And that's the reason why this is an equilibrium. But this equilibrium is not unique for this type of game. So for this set of players, we can have another equilibrium. So here on the right, I show another equilibrium. So in this equilibrium, the top link is used by I and L. So that has total load 9. And the bottom link is used by J and K. And the total cost is 7. So as you can see, this is not balanced as before, right? So here we have 8 and 8 balance. Here is not balanced, it's imbalanced. But there is nothing better the players can do. So, so if, for example, L switches, right? So if L switches from the top to the bottom, now the bottom will become 10, which is higher than 9. So L doesn't want to switch. For the same reason, I doesn't want to switch, right? Because it will increase. So 2 doesn't want to switch either. 2 doesn't want to go to the top because it will see cost 11. So all of these players are stable. They don't want to switch from this current situation. Okay, and that's another equilibrium. So there are 2 different distinct equilibria. Okay, somebody might say, okay, let's split the demand. Okay, let's have the players go have some demand on the top and some demand on the bottom. Okay, that can improve actually the situation. But even if we have splittable loads, we can still can have games where we can have we can still find Nash equilibria and situations in games where we can have multiple Nash equilibria. So in general, the question is, okay, so we can have different Nash equilibria. Which one is good and which Nash equilibrium is bad? And how we can characterize the quality of this Nash equilibria? So then Kuchipkas and Papadimitriou came up with this cost, which they call it price of stability and price of anarchy cost. So the price of stability, so for that, we need to introduce the notion of a social cost. Social cost is similar to some universal cost that we want to optimize in the game. And for our games, that's the worst player cost. So in the example games I described, the social cost for this equilibrium is 8 because that's the worst case, the worst cost for any player, which is 8. In this equilibrium, the social cost is 9, and that's because that's the worst player cost. So the price of stability now examines the social cost, the best social cost in any equilibrium. The price of anarchy examines the worst social cost in any equilibrium. So price of stability is the ratio of the smallest social cost in any equilibrium. And this example actually shows what's going on. So 8 is a social cost in this equilibrium, and this is the best equilibrium we can have in terms of social cost. We cannot have lower social cost than 8 for this game. 8 is a minimum. So therefore, the price of stability is 1 because we divide the social cost in the equilibrium with the best social cost we can achieve in any state. And so that is equal to 1. On the other hand, the price of anarchy looks at what is the worst case scenario. So it takes the ratio of the worst social cost in an equilibrium versus the best social cost in any case. In this is the worst equilibrium we can have. And so the worst equilibrium has social cost 9 versus, actually I should have divided by 8. I think I divided by 7 in this case. So actually the ratio here should be 8. It's 9 over 8 is the price of anarchy. Okay, so so as you can see, it's a small, it's bigger than 1. The price of anarchy is bigger than 1. But it's small. It's a small constant number for these games. And in their paper, Koutsouplias and Papadimitriou proved that the social cost is always 3 over 2 if you have 2 links. And if you have m links, the social cost converges to the constant 2. So it's always very small. And these are very nice games with a small price of anarchy. And so after the Koutsouplias and Papadimitriou paper, there were many other papers that extended this model and they introduced some other models. And one other natural, so most of the games considered network games, and some others considered parallel scheduling problem games in machines. But here in this talk, I focus on network games. So extending from one link to multiple links, now we have network with multiple links, because for example, I just saw a small network here with several nodes and links connecting the nodes. And now players choose paths over the links. For example, I have the red player picking a path from some node to another node, and a green player picking another path from one node to another node. And here we can extend the cost of a player by looking what is the total utilization on the edges. For example, in the red path, the total utilization is 6 because we're examining how many nodes, how many players are using the first edge, which is just 1. Then the second edge is used by two players, the third edge by 2 players, and the fourth edge by 1 player. So the total utilization is a sum of all of these, which is 6. And there are many variants. So the player cost is the sum of the utilizations of all the edges, and there are many variants of this game. For example, they consider here in the bottom splittable flow versus unsplittable flow. So in unsplittable flow, every player uses 1 path only. In the splittable case, they split. They can use multiple paths to send order demand along many paths. So that will be the splittable case. And then we have 2 types of equilibria: pure equilibria versus mixed equilibria. So pure equilibria is when a player chooses exactly one path. Mixed equilibria is when they have a probability distribution over many different paths. So, but in this talk, I just focus on pure equilibria, which is actually easier to discuss. And so most of these games, most of the papers have studied what is the price of anarchy and what is the price of stability, basically the quality of equilibria. But there is another set of papers which have studied how fast we can compute this equilibrium. So where we need to calculate the equilibria. So if it is a real life situation, we want to know how many steps it will take until the player stabilizes, right? Because we don't want to play the game forever. So and somebody would say, okay, let just the players play until it stabilizes. So, but if we do so, there are many game instances where we don't stabilize fast, and this can take exponential time until stabilization. So the question is if we can calculate such equilibrium states faster. So part of algorithm game theory is also about designing algorithms with the purpose of calculating Nash equilibria states. And this is actually what I will discuss today for a certain class of games. And there are exist algorithms that they can do this fast for the types of games I described earlier, but not for the game I'm going to explain next. And so here in the latest research I did on this topic, I examined bottleneck congestion games, where it's a variant of the games I discussed earlier. So the setup of this game is on a network. So we have a network. So here I have several nodes in the network. We have links connecting the nodes in the network. And what we have now is players. So every player, so I have here an example with 3 players, like I give them colors, which is the red player, the green player, and the blue player. Each player has a demand to say, each player has a demand DI, so player I has a demand DI. So they want to send some demand from a source to destination. Imagine like this is like a stream of packets they want to send from source to destination. Or they want to send a packet of a certain size equal to the demand. So all of them have to do that. And they want to, therefore, and in this game, I'm talking about a pure equilibria. All of them want to decide on exactly one path. And at the same time, they are not going, in some cases, they're going to split their flow. Some cases, they're not going to split their flow. If they don't split their flow, they pick one path to send all the flow from the source to the destination. So imagine now they pick some paths, but they overlap each other. Okay, this is the bad situation. They don't want that because that will delay the delivery of their demand. If they share the edges, that will slow down the delivery. So they don't want to share the edges. So here we can see that we have sharing of the edges. So their objective is to avoid sharing the edges. So they want to minimize sharing. But how am I going to express that? They want to minimize the worst sharing of an edge. So basically, that's the bottleneck edge. The bottleneck edge is the edge of their path that has the maximum congestion. And congestion, I simply measure it as a number of paths using the edge. So here, for example, in this specific edge, we have 3 paths crossing. So the congestion is 3. And this edge also has 3 paths crossing. So the congestion is 3. So, and that's actually these are the bottleneck edges. All the other edges are used by exactly one path. So the congestion on the other edges is 1. So the bottleneck edges are those that have the highest congestion. So let's look what else I can do. So this has high congestion. The bottleneck is high. Let's try to improve it. So the blue player can improve. So the blue player can pick another path, might be a bit longer, but the congestion on that path it's much lower. So instead of 3, it's just 1 because only one path uses the edge along the path. So the congestion is much better. So they improve. So the blue player has improved the situation. And that's what the players always try to do. However, in many cases, when a player tries to improve its own path, it may hurt other player paths. For example, if a player, the blue player, picks another path that overlap with the green, then that somehow hurt the green player. So, how more formally I define the game? So every player has a function which it tries to optimize. And I denote this with a small c. I is the player I. And S is the state. So in state S, what is the cost? S is a state which corresponds to a set of paths, the current set of paths chosen by the players. A player can pick any path in the network from the source to the destination. So the player of the cost of a player is basically the highest congestion along any of its path, any edge of its path. The social cost is the maximum cost of any player. Basically, that's the highest congestion on any edge of the network. And we're examining states where no player can improve further, so equilibrium states. So both of the states I showed earlier, so this is not an equilibrium yet.
Costas, did you see where Clement had a question on the chat? Did you?
Sorry, let me see. Oh, they don't want to share edges at all or at a given time. All right, so Clement, okay, thank you, Clement, for the question. So they don't want to share.
Maybe Clement can tell you what slide you're supposed to look at.
So,
which slide? Yeah.
Can you hear me?
Yes. Hi.
I think you actually answered the question. It's not like they go from the source to the target and then they're done and then anybody else can take those paths. It's like they have a stream from the source to the target, and at any given time, you don't want anybody to take one leg of that stream, like to share one leg of that stream at any given time.
So here is it's like first they are having a computation. They're having a time where they try to decide on the path, which path they're going to use. And once they decided, then they send the flow over the path. That's how that's the setup of the game. So here they're still deciding in what I showed. So the red paper, for example, can still somehow they send ping messages over the network to see what is going on.
Yeah, but somehow a ping has a beginning and an end. Like you send a ping and then you wait. Here you're looking at a model where you're actually streaming constantly. Like there's no interruption ever on that path. Yeah, in real life situations, actually, you observe the traffic while you are using the network. You're right about that. Yeah. No, but okay, thank you.
And then you can adapt. That's that will be the more accurate model. So here we abstract from that model to analyze it and see what can be done and what cannot be done. And but the real life situations can lead you to even worse scenarios than what I'm describing here. So somehow, you know, to analyze it, we have to model it in an idealistic way, which may not be 100% realistic. So let's continue. Okay, so why we examine bottleneck? So bottleneck congestion is important because it directly relates to the time it takes to send the traffic to the destination, to send the packets or whatever, the streaming packets to their destination. And another thing is that the higher the bottleneck, the higher the utilization of the nodes adjacent to the bottleneck edge. And if we're talking about battery operated networks, we don't want to congest the nodes too much because the energy will be depleted very fast on the congested node. So, and we want to, having lower bottleneck congestion is like doing load balancing. So minimizing the maximum congestion is similar to doing load balancing in the network. So in some previous, I studied this problem with a colleague, Magdon-Ismail, in 2009, and we examined what is the quality of equilibria we can achieve in such games. And in 2009, we observed that we can have price of stability 1, which means we can have very good Nash equilibria, which is with a quality equal to the best globally solution without playing game. So basically, the maximum congestion is equal to the best possible congestion we can get. And for that, how we can calculate those very good Nash equilibria states is basically we start with some global optimum, and then we let the players play until they stabilize. And that never increases the bottleneck congestion. It can never increase the bottleneck congestion. So whatever state we get is still optimal. So the bottleneck congestion is still very low. And that's why the price of stability is 1. But there could be equilibria which are very, very bad because the congestion, the bottleneck congestion on those equilibria could be really high. And here I have an example of such a game. Here, every player wants to send some traffic. So there is a player for every pair of in every edge. So for every edge, there is a player that wants to send the traffic from one edge to the next edge. For example, imagine a player that wants to send the traffic from here to here. Another player that wants to send the traffic from here to here. So there is a player that wants to send something to the adjacent edge. So of course, the best scenario is they just send it to the next edge. This is the best scenario, and this produces congestion 1. However, there is another state where instead of taking the direct link, take the link which is all the way around the ring. So that uses all the nodes, all the edges in the ring, except for one. And that leads to very long paths. And not only that, the congestion is the worst in that scenario because all of them are doing the same thing. And that means the congestion can grow up to the number of players. So we have this very bad price of anarchy, which gives a price of anarchy proportional to the length of the paths, the maximum length of the path they are using in the network, which in this case is proportional to the number of players. Okay, so price of anarchy is not very good in these games in general. And that makes it different from the other games with the sum of congestions I mentioned earlier. Another problem I studied recently with those games is the convergence. How fast can we compute the equilibria in bottleneck games? So for the other types of games I mentioned before, which was studied before, where the player cost is the sum of the congestions on the path, we know algorithms for how to calculate the equilibrium fast. But for bottleneck congestion games, it was an open problem. We didn't have good algorithms to calculate the bottleneck equilibrium very fast. In fact, this type of games, the bottleneck games, have been proven to be PLS complete. PLS complete is a variant of NP completeness. It's another complexity class. But still, it's very, so problems in this class are very hard to compute in polynomial time.
Okay, so I just had a question on the previous slide. I tried to ask in the chat, but
sure.
I was just confused by.
I had the chat, but I missed a question. Yeah.
You said that you noticed that in these networks, this price of anarchy was this very bad case because the nodes could all choose to send their traffic along that path that goes all the way around the circle. But I wondered, how would the players ever come to that equilibrium? Because somebody would have to make a really bad choice.
It doesn't come naturally. You're right. It doesn't come naturally. It just it exists. It can happen like I don't know. It doesn't. I mean, in a real life scenario, it can happen only if, for some reason, their obvious choice is not good. For example, if at the moment they want to pick a path, just sending along the shortest link, that link is congested, then they pick a longer link. You can imagine that happen that in a more dynamic situation.
Oh, so at some point, the link that goes directly to the destination is congested, so
yeah,
the node picks.
So at that moment, they may want to pick a longer path, which is a bit less congested. It could be like that. That could be a scenario in real, somehow motivation from real life scenario how it can happen. From a theoretical point of view, it's like, okay, what are the possible cases? And this is a possible case. It's
okay.
Like what would be the worst scenario?
And are you saying that that's an equilibrium scenario? Because
yeah, this is an equilibrium. Yeah, it's an equilibrium.
I would also think that if everyone is choosing the longest roundabout paths, someone could still improve their link speed by choosing the more direct path.
So if they do that, so if that player picks, for example, switches from the long path and goes back here, so you know all the other players are using this. So
yeah, but all the other links are just as congested, right?
Exactly. So if it goes here, there is no improvement. So basically, there is nothing to improve.
Oh, so path length doesn't matter?
So we're not, yeah, so in this problem, we're not taking into consideration the number of edges. So we're not summing, It's not like C plus something else. It's not congestion plus something else.
Well, I was thinking for each congested link you traverse, you would have to add more congestion.
So that's the other model where people add the congestions on all the links. So, but in the model I'm talking here, it's just the worst. So I'm basically looking at one edge. For example, this edge here, you have all the players except for one. N-1 players are going here on this edge. And that's the congestion. That's the bottleneck congestion, actually, N-1, if you have N players. And I'm not going to sum it for all the links. I'm not going to say N-1 plus N-1. I'm not going to do that. I'm just saying my cost is N-1 because that's the worst bottleneck. But if we did what you said, if I was summing, then yes, that's not an equilibrium because they simply switch here and it's much less the cost in that case.
Right, but if it's only the worst congestion that counts, then the length of the path doesn't matter and they would have no reason to switch to the shorter path.
Correct. And that's actually what leads to these very bad numbers for price of anarchy. So these games, bottleneck games, have very bad price of anarchy. The other games with the sum of congestions have much better price of anarchy.
Okay.
Because of this symbol distinction, yeah.
Okay.
Yeah.
Now I get it.
For this question. All right. So for how fast we can find equilibria, like one of the two equilibria I mentioned earlier. I mean, for some scenarios it might be easy to find them, but there could be situations where it's harder. So this finding a nice equilibrium is typically a very costly. It's not easy. It's PLS complete. It may take a lot of time. If you let the players converge, it may take exponential time to converge to a stable state. If you try to design an algorithm, that's also hard. And there is no, it's difficult to design a precise algorithm to give an equilibrium, to calculate an equilibrium in polynomial time. And so what we do is we focus on approximate equilibria. So we don't care anymore with a player precisely being stable, but we have the notion of astable. Like this is an approximately stable player. A player is astable as long as any other move cannot improve its current situation by more than a factor of A. If there is an improvement of factor of A, then it's going to take the move. Otherwise, it's stable. If all the players are astable or approximately stable, then we have an approximate Nash equilibrium. The reason we're looking at approximate Nash equilibrium is the same reason why in optimization we're looking at the approximate algorithms, because getting the precise solution, we may not get a polynomial algorithm, but looking for the approximate solution, we may get a polynomial time algorithm. So, and therefore, looking at the approximate equilibrium, we got a result. Basically, we found an approximation for a Nash equilibrium. We got a logarithmic approximation, an order log m approximation. So basically, every player is approximately stable by a factor of log m. So they cannot improve by more than a factor of log m from their current local state in that equilibrium. And we can calculate, basically what we're doing, we're calculating a path for every player so that each player is approximately stable. And we do that for one case where every player has uniform demand. And then there is a more difficult scenario where players have non-uniform demands. And uniform demand means every player has exactly the same demand di. For example, then you can normalize it to 1. In the non-uniform demand, different players have different di. For example, if di, dj, and di is different than dj. And in both cases, though, we get an approximate equilibrium. The expression in the second case is a little more complicated. And so let's see. And not only that, one other thing I want to mention here is the price of anarchy. I mean, the quality of this equilibrium is very good. It is almost optimal for these games. So let me just go on overview of the technique. So the main technique we use here is we first consider the splittable case. In the splittable case, every player can split its demand along multiple paths. So instead of picking only one path, it can split the demand among multiple paths, similar on what we do in classic flow problems. And then I'm trying to minimize the maximum load in such a setup in the splittable case. And here, we can calculate a precise mass equilibrium in the splittable case. And then after that, I use a technique called randomized rounding to convert the splittable scenario to an unsplittable scenario. So every player, instead of splitting, now picks one random path along the splitting, and that's the answer for the player. And that will give me a pure Nash equilibrium. That's basically the overview of the technique. Randomized rounding is not a new technique in approximation algorithms, but the way we use it here to compute a Nash equilibrium is a new technique. And in the remaining time, I will try to give you an idea of what we try to do. My slides are not going into very big depth of the approaches. I'll just give an overview of the two approaches and then conclude. So let's talk first about the splittable case. So to approach this problem, as I said, instead of looking at an individual path for each player, I'm going to assume that every player splits the demand. So every player sends a demand among multiple paths instead of only one path. Similar to what we will do in regular flow problems. By doing so, I can I can load balance the total utilization of the edges. Basically, I can minimize the maximum utilization of the edge by expressing it as an LP problem. And this is basically a multi-commodity flow problem, and LPs can be used to find solutions for such problems. So LP is a linear programming formulation of the problem. So the basic approach is we formulate the problem as an LP where we minimize the bottleneck congestion. And then we look at the edges that have the highest congestion, the bottleneck edges. So let's see that highest congestion. C is basically the edge that is used by C players. And suppose that's a maximum utilization of any edge. And then we find some players along those edges which are stable. They don't want to switch strategy. They don't want to find any alternative path. Then what we do is we freeze those players. Basically, we fix those players, saying those players cannot have anything better. So we fix their assignments. We fix their flows. And we formulate these flows as constraints for other players. And now we again run the same idea. In the residual graph for the remaining players, we again formulate a new LP, but now the maximum congestion C is going to be lower. And every time I identify a new set of players which are stable, and then I remove those players, and I repeat this game until there are no more players to consider. And eventually, the whole process stabilizes in a polynomial number of steps. So if I can give an overview of this approach. So this is the formulation of the LP. This is a classic formulation. The most important thing here is the F here are the flows of players. So every player I has some flow from a source to destination. And what I'm describing here is a classic I'm just giving the equation here. I'm not going to give it in a very big detail. It's a classic formulation, LP formulation to minimize the maximum congestion on the edges. So this is a multi-commodity flow problem, and this is this is a classic formulation. I mean, it's not only in my paper. You can find this in other papers. I just wrote it down to take into account some players that are stable and some edges I have removed from the graph. And so once LP can find a solution to this minimization problem in polynomial time. Okay, this is a known result. If I had integer programming, then I wouldn't. That doesn't necessarily give me a polynomial time, an answer in polynomial time. But LP gives me an answer in polynomial time, and that's why we're using this approach. And what does it give me? So after I run the LP, what I get is a set of flows for every player. And if you look at the flows on the different edges on the graph, we see that some edges on the graph have maximum utilization. So here I pick those edges. Suppose the maximum utilization is C. That's the maximum congestion. That's the bottleneck congestion. So a few of the edges in the graph have the bottleneck congestion C. Let's look. Some of the players have sent their flows along those edges when we solve the LP. Some of the players are happy. Some of the players are not happy. Some of the players may have a better option. Okay, so for example, a player I may have sent its flow, some of its flow along this edge. It could be all of the flow along that edge or some of its flow along that edge. So the player I may be happy. If the player I is happy, then the player I is stable along those edges. But the player I may not be happy. The player I may have an alternative solution where if he, instead of sending the flow along that edge, he sends the flow on another edge, say on some other edge, it can get a lower flow. It can get a flow, it can get a cost, say for example, with a C prime. So suppose that the flow it was sending here was epsilon. And then that epsilon moves from here and it goes here. So when it goes here, so that edge before had C prime, now we add the epsilon, but still, the new flow on that edge is smaller than the flow before, so it's smaller than C. So instead of C, the player I experiences C prime, which is smaller than C. Okay, so moving its flow from one edge to another, it can lead to a smaller, congestion for the player. So now player happy is more happy with this situation, which means that in those edges with maximum congestion, some players are unhappy and they may switch. They may wish to switch if we let them choose something better. Okay, let them all switch. Let's keep doing that. Take the players along those edges with a maximum congestion and let them switch. Okay, let's keep doing that. We will find that we can remove some players from those edges, but we cannot repeat that. We cannot keep doing that forever. At the end, we will find that there is a subset of the players that use those edges that cannot be removed. For those players, there is no better alternative. And the reason why is that, it is that if all the players were removed from those edges, then that would not have been the maximum congestion. The maximum congestion on the whole graph would have been something smaller than C. Then the LP wouldn't give us the correct answer, right? So because of that reason, there must be some edges where the players are happy on those edges, on the maximum congested edges. So those are the players that we keep. So we identify those players, we call them the K players. This is a set of players K, which are stable on the maximum congested edges. So those players, we keep them, we freeze them, and then what we do is we keep those players on those maximum congested edges. We freeze the flows that were going through those edges. And actually, those players are removed from the game. They're not going to be allowed to play in the subsequent rounds of the game. So what we're left now is with the remaining unstable players, which use all the other edges on the graph. And those are all the other edges which either have C congestion, which are unstable, or lower than C congestion. And we'll repeat this process until all the players are stable. So what happens at the end is, if we repeat this process in so what we do, we run the LP formulation. We identify a set of players K1 which are stable. Right? Then we remove these from the game and remove the corresponding maximum congested edges from the game. Then we run another LP formulation on the residual game, then we get another set of stable players, K2, on the new maximum congested edges. And then we repeat this until there are no more edges left in the graph and no more players are left in the graph. So eventually this stabilizes because all the players will be stable with this process. And also the way we solve the problem is we calculate the mass equilibrium at the end, because all the players are stable. The price of stability, this is a very good mass equilibrium. So it's optimal because the LP always gives you optimal congestion. And also it works on different demands. And the whole process takes polynomial time because, as I said, the LP takes polynomial time. In every iteration where I apply the LP, I remove at least one player and at least one edge. And so the total, so the number of iterations of the whole process is proportional to the number of edges in the graph or the number of players. So eventually it stabilizes in polynomial time. Okay, that's the explanation. But okay, that works very well for splittable equilibria. But how about unsplittable equilibria? I'll just give you in a couple of slides the overview of the idea. What do we do with the unsplittable case? So I told you before, we are going to do randomized rounding. So first we solve the problem for the splittable case. Now, in the splittable case, every player has split the demand over multiple paths over the graph. So instead of having only one path from source destination, it can have multiple paths where it splits its flow along those paths. So there is one technique used in flows. It's a typical idea that it can convert the splittable flow to a set of paths for every player. So every player now can split the flow over a specific set of paths. And it's like setting some flow on one path, some flow on the other path, some flow on the third path, and so on. This is called path decomposition. But the way we see it here is that the flow on every path corresponds to a probability. It's the probability of using that path. So now this now gives the idea of doing randomized rounding. So randomized rounding maps all the flow of the player, all the demand of the player to one of those paths. And what's the probability of doing that? So the probability to pick the path is equal to the flow of the demand on that path. So the flow on the path is equal to probability. And that's randomized. This technique is called randomized rounding. It's not new. I mean, other people have used it to approximate problems on networks. But what is new here is the way we use it for calculating Nash equilibria. And the new part also is the repetitive LP formulation until we'll calculate all the stable players. But because of the randomized rounding, we lose something. We lose the precision. So instead of getting a precise solution, instead of getting a precise Nash equilibrium, we get an approximate Nash equilibrium because on the expected case, we expect the congestion on the edges not to increase with the randomized rounding. But we cannot prevent, in the worst case scenario, it might increase. Using Chernoff bounds, we can bound by how much the congestion is going to increase. And we can prove it doesn't increase by more than a logarithmic factor. So that means that every player is approximately stable by a factor of log m. So they cannot improve more their congestion by more than a factor of log m. And that gives us a log m approximate Nash equilibrium. And that's basically for the case. So this works very well for the case where all the demands of the players are the same. And also, we extended the same idea for the case where the different players can have different demands. And it's exactly the same idea where, but the randomized rounding doesn't work very well there because when you are converting the flows to paths, some players may become unstable, and more precisely, the players with higher demands may destabilize players with lower demands in this situation. But we can still solve the problem by separating the players according to the demand. So we treat separately the players with higher demands than the players with lower demands. And then we again have different rounds to solve the problems with respective LP formulations according to this decomposition with the demands. And at the end, what we're getting is another approximate Nash equilibrium where now the expression depends also on the ratio on the demand. So dmax over dmin is a maximum ratio of demand. So when you take the logarithm of that, we have this parameter z. But at the end, we get a polylog factor approximation for the whole problem. And that's basically the whole idea. And now I've reached my conclusions. So basically, to summarize what I presented here, so I somehow summarized, presented in this class a summary of all my work on algorithmic game theory. I presented some results on price of anarchy and price of stability, which is a part of work that concerns the quality of Nash equilibria. How good are Nash equilibria compared to the global optimum of the respective optimization problem. And also I presented results about how fast we can calculate Nash equilibria. And I've shown these approximations where we cannot exactly calculate a precise Nash equilibrium fast, but we can calculate a very close Nash equilibrium fast. So in the future, so some future directions in this area, of course, we can keep looking at network games, and specifically bottleneck congestion games. So we can assume that different players have different cost functions on the edges. So for example, I assume here that every player has the same function on the bottleneck. For example, it's simply the sum of the paths using an edge. But you can imagine one can have a linear function on the congestion, another can have a non-linear function on the congestion, and generally different players can have different functions on the congestion on the edges. And another thing, maybe like Edward mentioned, how about if we add a different metric? For example, let's add the path length. So for example, we prefer shorter lengths than longer path lengths. In fact, actually, I've done a work on this area where instead, not only so we had a model where we not only looked at congestion, but we added the path length in that case. And we showed that there are, the only problem with those games is that there are scenarios where we cannot have Nash equilibria. So if we add the path length, the games may not stabilize. But if they stabilize, we analyze the price of anarchy on those games. But in general, in the future, I want to look at game theory on blockchains. So now I've started looking at some blockchain problem formulations with the hope that we can bring this research from networks to blockchains. And as you know, part of blockchains are networks. So several networks like Bitcoin, Ethereum, they're working on networks. And then we have different players interacting with each other. But the purpose is different. So we have to adapt whatever we know from the algorithmic game theory to the new setup of blockchains. And we'll see what kind of new results this will bring us. And with that, I'm concluding my talk. And thank you very much for listening. Don't know if there is any question.
Thank you very much, Kostas. So does anyone have any additional questions?
Thank you.
All right. Well, it would seem no. So, I mean, you had some questions during the thing, so that's good.
Yes.
Thank you again for an interesting talk, and I'm sure everyone enjoyed it. I know I did.
All right. Thank you very much for hosting me.
Have a great weekend.
Thank you. You too.
And thanks everybody else for coming to the 5th colloquium, I think it is now.
All right.
Bye.
Okay. Bye bye.